Welcome to a new episode of AI Research Radar, where we showcase the most cutting-edge developments in the field of artificial intelligence. Join us as we shine a spotlight on the latest advancements and breakthroughs in AI research. From machine learning to natural language processing, AI Research Radar covers it all to keep you informed on the forefront of AI innovation.
The paper titled LLM-Coordination, Evaluating and Analyzing Multi-Agent Coordination Abilities in Large Language Models by Ogoshe et al. Introduces a comprehensive framework for evaluating the coordination capabilities of large language models, LLMs, within the context of pure coordination games. The primary contribution is the development of the LLM coordination benchmark, which includes two distinct tasks: agentic coordination and coordination question answering, QA. Agentic coordination. This task is designed to evaluate LLMs in their capacity to act as proactive participants in four pure coordination games. It involves integrating LLMs with a cognitive architecture for coordination, CAC, allowing them to interact directly with game environments. This setup tests the LLM's abilities to understand game rules, make strategic decisions, and effectively cooperate with other agents, including both AI and human partners. Coordination QA. This component assesses the LLM's comprehension of the game environment and their reasoning capabilities through a series of 198 multiple-choice questions derived from the coordination games. The questions are designed to test three critical areas: environment comprehension, understanding of game dynamics and rules; theory of mind, TOM, reasoning, the ability to infer the intentions and beliefs of other players; joint planning, capability to make strategic decisions that consider the actions and plans of other agents. Additionally, the paper introduces the cognitive architecture for coordination, CAC, framework, which is pivotal in enabling the integration of various LLMs into the game environments. The CAC facilitates the translation of game elements into textual formats that LLMs can process, and it incorporates features to enhance coordination, such as memory modules for retaining important game details and reasoning modules for decision-making support. The experimental section of the paper is structured around evaluating the performance of LLMs equipped with the proposed methods across different game scenarios and setups. The primary experiments are categorized into self-play and cross-play settings to assess both the intra-model coordination and the inter-model adaptability of LLMs in unseen partnerships. Self-play experiments. These experiments involve LLMs coordinating with copies of themselves. This setup tests the model's baseline coordination capabilities in a controlled environment where both agents have the same operational logic. The metrics focused on other models' abilities to achieve game objectives without external influences. Cross-play experiments. In these experiments, LLMs are paired with agents they have never interacted with before, including other AI models and human players. This setup is crucial for testing the adaptability and robustness of the LLMs in dynamic, real-world-like scenarios where they must adjust their strategies based on the actions and behavior of unfamiliar agents. The games used in the experiments, Hanabi, Overcooked AI, Collab Capture, and Collab Escape, each present unique challenges that require varying levels of strategic planning, communication, and mutual understanding among agents. The performance of LLMs is evaluated based on several metrics, including game scores, successful completion rates, and the qualitative analysis of interaction strategies. Results from these experiments provide insights into the strengths and limitations of LLMs in coordination contexts. Key findings include the observation that while LLMs exhibit strong environmental comprehension, they struggle with complex theory of mind reasoning and joint planning tasks. The experiments also highlight the potential of LLMs to outperform traditional reinforcement learning methods in specific coordination scenarios, particularly when common sense understanding and adaptability are critical. Overall, the experimental work detailed in the paper provides a thorough validation of the proposed methods, demonstrating both the capabilities and the areas for improvement in using LLMs for complex multi-agent coordination tasks.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper, LLM-Lingua-2, Data Distillation for Efficient and Faithful Task-Agnostic Prompt Compression, introduces a novel approach for prompt compression in large language models, LLMs, focusing on task-agnostic compression to enhance generalizability and efficiency. The authors address the challenges posed by traditional methods that rely on information entropy and unidirectional context, which often fail to capture all essential information for effective compression. The proposed method centers on a data distillation process that extracts knowledge from an LLM to compress prompts without losing crucial information. This is achieved by treating prompt compression as a token classification problem, where each token in the prompt is classified as either preserve or discard. The classification is based on a transformer encoder that captures essential information from the full bidirectional context of the prompt. Additionally, the paper introduces a new extractive text compression dataset that focuses on retaining essential information necessary for LLMs to perform effectively in downstream tasks. This dataset pairs original texts with their compressed versions, providing a valuable resource for training and evaluating prompt compression models. The compression model operates with smaller models like XLM-RO-BERT-large and MBERT, which are trained to explicitly learn the compression objective. This approach not only ensures the fidelity of the compressed prompt to the original but also significantly reduces latency by using less computationally intensive models. Experimental work used to validate the methods. The validation of the proposed methods involved extensive testing on both in-domain and out-of-domain datasets, including Meeting Bank, Long Bench, Zero Scrolls, GSM-8K, and BBH. The experiments were designed to assess the performance of the compression model across different settings and compare it with existing baseline methods. In domain testing, the model was first tested on the Meeting Bank dataset, where it showed significant improvements over existing methods in terms of compression efficiency and the quality of the compressed prompts. The effectiveness of the model in retaining essential information was particularly noted, with high fidelity to the original prompts. Out-of-domain generalization. To evaluate the generalization capabilities of the model, it was tested on various out-of-domain datasets. The results demonstrated robust generalization ability, with the model performing well across different types of data and tasks. This was indicative of the model's utility in real-world applications where it can be applied to a variety of LLMs and scenarios. Performance metrics. The experiments utilized several metrics to evaluate performance, including the speed of compression, the fidelity of the compressed prompts, and the overall effectiveness of the model in facilitating LLM tasks. The model consistently outperformed baselines, offering a 3x-6x speed increase over traditional methods and improving end-to-end latency by 1.6x, 2.9x with compression ratios of 2x, 5x. Dataset contribution. The new extractive text compression dataset played a crucial role in training and validating the model. It enabled the precise measurement of the model's ability to preserve necessary information in compressed prompts and facilitated comparisons with other compression approaches. These experimental results underscore the effectiveness of the proposed task-agnostic prompt compression method, highlighting its advantages in terms of efficiency, generalizability, and fidelity, which are critical for practical deployments in diverse LLM applications.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper titled Stream of Search, SoS Learning to Search in Language introduces a novel methodology designed to advance the capabilities of language models, LMs, by teaching them to effectively search and backtrack during problem-solving tasks. The primary focus is enhancing the LM's ability to handle complex decision-making and reasoning, which inherently requires sophisticated search capabilities. The method leverages a novel representation called Stream of Search, SoS, which is essentially a serialized string that captures the search process. This technique involves portraying the entire search process, including exploration and error recovery, as a flattened text sequence. This representation is designed to train the language model not just on the outcomes, but on the process of reaching those outcomes, incorporating mistakes and the steps taken to correct them. SoS is built upon a transformer-based architecture, which is pre-trained on a dataset of search streams generated by heuristic solvers. The training data includes diverse scenarios from the game of Countdown, where the goal is to reach a target number using a set of given numbers through arithmetic operations. This approach contrasts traditional training methods that typically focus on the final, correct answer without exposing the model to the intermediate steps, errors, or backtracking that are crucial for developing effective search and planning strategies. Moreover, the paper discusses the implementation of two policy improvement techniques post-pre-training: advantage-induced policy alignment, APA, and self-taught reasoner, STAR. These methods are aimed at refining the model's search strategies by focusing on improving correctness and efficiency in problem-solving. The experimental validation of the methods proposed in the Stream of Search paper involves a series of tests designed to assess the effectiveness of the SoS approach in improving the problem-solving capabilities of language models. The experiments are structured to evaluate both the base model trained on the SoS dataset and the effectiveness of subsequent policy improvements through APA and STAR. Base model training and testing. The language model is pre-trained on a dataset generated from multiple heuristic solvers playing the game of countdown. This dataset includes 500,000 search trajectories, which represent diverse and suboptimal search paths to solve the game. The model's performance is tested on both seen and unseen problem sets to evaluate its generalization capabilities. This testing assesses the model's ability to generate correct solutions and its efficiency in exploring search paths. Policy improvement experiments. Following the pre-training, the model is fine-tuned using two different reinforcement learning strategies, APA and STAR. These techniques are intended to enhance the model's ability to find solutions by focusing on trajectories that lead to correct outcomes. The fine-tuning process is iterative, with performance metrics evaluated at each step to determine the effectiveness of the policy improvements. The model is tested again on seen and unseen problems to measure any enhancements in accuracy and search efficiency. Comparative analysis. The results from the SoS model are compared against traditional models trained only on optimal paths. This comparison highlights the benefits of training on full search trajectories, including mistakes and backtracking. The experiments also compare the alignment of search strategies between the SoS model and the strategies used to generate the training data. This analysis helps in understanding how closely the model mimics or diverges from its training data in terms of search strategy effectiveness. Evaluation metrics. The primary metrics for evaluation include the accuracy of the solutions generated by the model, the alignment of search strategies, and the efficiency of search, measured in terms of the number of states explored before reaching a solution. Additional analyses focus on error types encountered during the search processes, such as arithmetic errors and exploration errors, providing deeper insights into the model's operational strengths and weaknesses. Through these experiments, the research demonstrates that language models can significantly improve their search and problem-solving abilities when trained on comprehensive search trajectories that include the process of making and correcting errors. The findings suggest that such training not only enhances model performance but also equips LMs with more flexible and robust search strategies, potentially enabling them to discover new methods of problem-solving.
Thank you for joining us for this episode of AI Research Radar. Be sure to stay tuned for our next episode where we will showcase the latest innovations in AI research. If you enjoyed the content, please consider subscribing and liking the video.